I expect your complete cooperation. So this is part of an experiment through MIT's OpenCourseware to be able to I think it's, the philosophy is something like have a few lectures per course available, or at least pieces of lectures available, just to add more color or to add more of a sense of reality to course offerings on to the course materials, so that they not only people, instead of just downloading PDF file after PDF file after PDF file, people really feel it's part of a real course. I don't exactly know all the details, but I know that. So I was asked if I would participate in this, and I agreed. 1, 2, 3, 4, 5, 7, 8. So let's see. You guys are probably very eager to find out what the next assignment is. So this is due next Thursday, which is the 22nd. And these are problems from the duality handout. Okay? So I presume everybody's downloaded the duality handout and has it printed. Who does not have the duality notes with them for today's class? Okay, good. All right, so while we're waiting for some students to mosey on in, and also I was supposed to have overhead for today's class, which I do not have, which is a little unfortunate, but what the heck. I will be able to deal without it, I hope. So let me ask you a question. Where have you seen duality? What's one place most of you have seen duality? Come on.
Well, we just saw duality in interior points.
For linear programming. So, I mean, we didn't see interior point duality. We just saw LP duality.
Derivation of the interior point we talked about.
Okay. So linear programs have duals. Okay. Where have you seen duality other than in linear programming? In some way, shape, or form.
Support vector machines.
Huh?
Support vector machines.
Support vector machines. Ah. So, okay, where have you seen support vector machines?
For quadratic programming.
Okay, and where have you seen that?
In machine learning.
Yeah, in a course here you took, or?
Yeah, at MIT.
At MIT. Okay, so that's right. So if you know anything about machine learning, as Alan does, and in fact I do, which is fortunate. So the machine learning problem, actually one way to set it up, the pseudo-natural way to set it up is as a convex quadratic program, and then you actually wind up solving the dual, which also happens to be a convex quadratic program. All right, so that's duality and optimization. Okay, where else have you seen duality? And forget optimization. Dan.
Game theory.
Game theory. Right, you got your row and your column players, your minimax. What is the mantra of game theory? Minimax equals maximin? Something like that? Okay. So who invented the name? This will be on the final. So who invented the name minimax? Anybody know? No. It was actually Tucker who came up with the name. This should be called, and actually he was going to call it the max-min-min-max theorem. And Tucker said, no, let's give it a nice name. Call it the minimax theorem. It had a nice semantic ring to it. Okay. All right, so in game theory, there's duality in game theory. Some of you just came from game theory, right? How's duality doing there?
It's pretty good, I think. Yeah.
Okay, good.
Not at all.
Good. Where else? Come on. Who has studied electrical networks? None of you? Really? I can't believe if I'm the class expert on electrical networks, we're in deep trouble. Okay. So, Hamid. Waleed. I knew it wasn't Hamid, actually, but I couldn't place whatever. Waleed. So where have you seen it in electrical networks?
Well, in physical systems in general, flow and effort variables are sort of dual variables.
Yeah, there you go. So like I think you have like, currents are primal variables, and then potential differences,
For example.
Okay. How many of you have studied truss structures in mechanical engineering? Elisa. So what are the primal and dual variables there that you can remember? You don't even know. So you remember some of the variables in the system being the forces in the system. And what are the duals? What wind up being the duals of the forces? Anybody know? The tensions. That's right, or the displacements, I guess. All right, now we're getting a little this is a little sad because I'm lecturing on this evening. I got to review my notes. They're right in my bag there. Okay, so let me give you a couple more examples, actually. How many of you have worked? How many of you have ever visited a manufacturing plant? Okay, great. And so, Pravita, what did they manufacture in that plant?
Bikes,
Bicycles?
the two-wheeler motorbikes.
Oh, two-wheeler motorbikes. Okay. All right. So you were seeing duality there, actually, because, so what is the dual of production variables? Take a guess. Who said price? Teo said price. That's right. So usually prices and production are dual in economic models. So duality is kind of everywhere. But then actually duality in optimization has a funny non-history in the sense that, so LP duality was first observed by von Neumann, actually, and more formalized by Tucker and Gale and Kuhn. And believe it or not, Danzig, when he developed the simplex method, von Neumann showed him all of this duality stuff, and he thought, who cares? Okay, that he sort of thought it's really irrelevant. It's just some mathematician's whims. Okay, that he thought it was completely irrelevant to linear programming. Actually, now he then, right? Who developed who developed price-based decomposition methods? By the way, dual price-based decomposition methods. Danzig. Okay, so he changed his tune on that very quickly. But then people tried to extend duality theory from linear programming, and the first real attempt at that from a practical point of view was the dual of quadratic programs, which was developed by don't write this down, which was developed by Richard Cottle, and then Philip Wolff, who is still at IBM, I believe, then came up with a general scheme for duality that kind of worked, but it really didn't. Okay, and oddly enough, it wasn't until the late 60s and early 70s that sort of what I would call modern Lagrange-based constructive duality theory. I'm going to put constructive in quotes, okay, because as you will see here, we aim for a constructive theory. And in fact, without being able to construct things, our theory, to a certain extent, is useless. Okay? And sometimes we can construct, and you'll understand shortly what I mean by construct. Okay? Sometimes I can always write down on paper something called a dual for any optimization problem. But whether I can actually construct it, work with it, get closed forms for something in there, that's a matter of individual problem settings. And so the theory as we now understand it, and as I now present it to you, was actually first formalized in a paper by a guy named Art Jeffreyan, who was at the business school at UCLA. And actually, so Jeffreyan wrote this beautiful theoretical paper that really just became a fantastic monograph for duality theory, and then left all that stuff and did sort of, well, what do managers really need to know to be successful in life, and all this. And I ran into Jeffreyan 10 years ago at a conference, and I told him I was using all of this stuff in my PhD course in nonlinear optimization, and I could tell he was both flattered and bewildered. And I think he was flattered that some of his old stuff was being used, but I think he was bewildered because he had completely forgotten what it was. So anyway. All right, so let's take a look at all of this stuff. And we will see pretty soon some very important, let me see, I've got to figure out a blackboard plan here. I'll try this starting over here. Some of the usefulness of duality theory, and duality theory is beautiful and useful, okay? And, well, we'll see all of that pretty soon. Okay. Actually, before we get started on that, I'm just going to give you some warnings about plus and minus infinity. Okay, and I'm just sort of going to read from the notes. So if I have a problem that says max f of x, okay, subject to x is in some set. That's just a problem. I can redefine some function h of x to be f of x when x is in S, and to be minus infinity otherwise, right? Okay. And then I could recast this problem as the same as maximize h of x, x in all, Rn. Okay? Right? Clearly that's true. But there's actually a little bit of a lesson in all of this. And sort of the lesson is that it's going to get a little, you sort of think, well, okay, any x is feasible for this problem. Okay, but only x's in S are feasible for this problem. So we're not going to make the distinction, right? So that if I'm maximizing and my h function takes on the value of minus infinity, I might as well call it infeasible. Okay? So that if I'm maximizing and things take on the value minus infinity, I'll call that an infeasible point. Okay? And I can go the opposite. If I have some function h that takes on that, well, I'll do it a little differently here. So, yeah, if I have some, get the eraser. If I have some problem, I got to get my notes here. If I'm maximizing some k of x, okay, as subject to x is in Rn, okay, and suppose k of x equals infinity for any x that's not in the set S. Okay, then I might as well rewrite the problem as maximize k of x subject to x in S. Okay, and I can do the same thing with minimization, where I would replace minus infinity by plus infinity, stuff like that. All right, so that's just a bit of a warning. Okay. All right. So now let's study our problems. Actually, I'm going to make one other comment first, which is we're going to be looking at optimization problems. You can sort of think, I might as well work in minimization format. Minimize over x. And then I got a bunch of GIXs, and I'm going to say I got some bigger than or equal to, I got some less than or equal to, I got some equality constraints, and I have some other constraints that say x must lie in some set. And I will call this the ground set. Okay? So capital X will be the ground set. Okay? And without loss of generality, for convenience of exposition, I'm going to assume all my constraints are less than or equal to constraints. Okay? And so I'm just going to write things like this. Okay? And so actually, let me write that over here. So OP, my optimization problem, is going to be minimize f of x subject to g of x less than or equal to 0. There's a bunch of constraints, and x is in my ground set. Okay. And actually, the tricky thing in duality theory is what we call the constraints and what we call the ground set. Okay. So this ground set, for example, okay, this could be Rn, okay. It could be what we call Rn plus. This is the non-negative orthant. Okay. It could be the non-negative integers. Okay. It could be some other constraints I equal m plus 1 through m plus something like that. That is, yes, Dan.
So what is our motivation for writing X instead of just putting those constraints in?
You will see that shortly. Okay? So that, in other words, so what we decide to call the constraints and what we decide to call the ground set will determine what the dual looks like. Okay, so that notice, it will not be the situation where every problem has a unique dual. Okay? If I hand you a problem, if you call these constraints the ground set and these constraints the other constraints, you'll get a different dual than if you did it the other way around. Okay? So that there is more, that is, it's how we set things up that's going to determine the dual. Now,
Taking the dual only of 7 constraints.
you can think of it that way. This will become, I hope, very clear to you very shortly. Okay? And by the way, my ground set could also be some polyhedral set. Right? I mean, for that matter, it could be anything I want. Okay? All righty. So here we go. So let's define the dual for this problem. Okay? So this was the primal. Okay. So watch what we're going to do. The first thing is we're going to form something called the Lagrangian. Okay? And what we're going to do is we're going to take these constraints, you can think of these as the explicit constraints, and we're going to pretend we are economists, in a sense. We're going to sort of say, why have government regulations when if we just found the right price, people would naturally do things efficiently? Okay? So I'll define my Lagrange function to be f of x plus, I'm going to assign price, you can think of these as prices to each of my constraints. I'm going to take them, I'm going to put them up in the objective function with prices associated with them. Okay? Or the other way to write this is just f of x plus u transpose g of x. Okay? So that's my Lagrange function, or Lagrangian as it's called. Okay? Now that's the first step. There's 3 steps in forming a dual. All right? The second step is to sort of construct what's called the dual function, which I call L star of u. And that function is the minimum over all x in x of L of x u, which is the minimum over all x in x f of x plus ut g of x. All right, so let's pause. Okay? And let's stare at this for a minute. And I have the following warning for you. Okay? I will be doing no complicated mathematics in this lecture. Okay? None. Okay? But a lot of the way I do things will be different. And so that's why we're going to have to pause and look at things. All right? Because there's nothing, right? You know, I've not invoked Ito calculus here or Tarski's lemma or, anything like that here. But you could sort of think of, instead of solving this optimization problem, I have chosen, think of the u's as prices if you want to be concrete. I've chosen, think of these variables as, think of these constraints as, I can't use more labor than I have available. I can't use more steel than I have available. Something like that. And then sort of think, rather than have those constraints, if I just internally charge myself for labor and steel, maybe everything will work out. So I assign some prices, okay, and then I move this into the objective function at this price level, and I solve this problem, okay? And this is for a fixed set of prices, or a fixed dual variable u. What makes this theory constructive is when I can solve this problem conveniently. And that either means in a closed form or through some other mechanism that I view as simple. And we'll see that shortly. Okay? But in other words, I get a that this expression here, equivalently here, is easy to evaluate. And if it's not easy to evaluate, I'm sunk. Okay? I mean, I can develop a beautiful theory and prove nice theorems about it and everything else, but it's not going to be a constructive theory, okay, without the ability to solve this problem efficiently. All right? And then the dual problem, so you can think of, I'm building a function here. For every set of u, this solution to this minimization problem gives me a value, and now I have a function, okay? And then my dual problem, I'm running out of Blackboard room, my dual problem, D, and I'll call that V star, is going to be maximize L star of u subject to u non-negative. And that's the dual. That's all there is to it. Actually, let me put Z star up here. Okay. My primal optimization problem, I formulate the Lagrangian. Okay. I create the dual function, and then I set up the dual problem. Okay. Now, mind you, at the moment, this is literally just a bunch of, it's not Greek, but it might as well be. Okay. So let's look at some examples. Okay. So one example, I want to do two examples with you, and then you have a bunch of homework problems. Oh, speaking of homeworks, by the way, so does anybody have any questions? It's a little late on this, but everybody got my email, right? I thank one of the class members for sending me this note about the potential problem with that exercise. Who was it who sent me the note again?
It was in your other phone.
Don't scare me like that. Oh no, I'm supposed to be there right now. I just got to remember in my brain who it was, and I don't remember at the moment. Okay. All right, so let's do some examples. So let's look at linear programming. Okay? And then this will give you a flair for how some of this is going to work. So let's look at min cx, ax bigger than or equal to b. Okay? Now, here's what I'm proposing to do. I'm going to do this first, slowly with your help. And then the second one, I'm going to invite, well, I don't know. We'll see how this goes. So just watch. So suppose I want to get, by the way, who can tell me what the LP dual of this better be by the time we're done? Who knows the LP dual of this problem? Somebody. You don't know your LP duality rules? Claire. Sorry. Karine.
Yeah.
Yeah.
Since max P transpose B subject to A transpose is equal C and
Sign of P?
greater than
Good, good. Okay. So hopefully we'll get here, right? But let's do it based on this theory here. So let's just see how it works, okay? So the first thing I'm going to do is I'm going to take ax bigger than or equal to b, and I'm going to write it as b minus ax less than or equal to 0. And that way I've got less than or equal to 0 constraints. Okay? And so Claire was so helpful. So now this is the problem here. Ashish. I knew that. Okay. So Ashish, what's the Lagrangian for this going to be?
That's going to be C times X
Right?
plus U transpose B minus AX.
Good. Right? That's the Lagrangian. All right? I can rearrange that to be B transpose U plus C minus A transpose U transpose X. I'm doing that on purpose. Okay. Actually, Ashish, we should have backed up, right? We should have said, okay, if that's the problem, we're going to call these the G's. Okay. And then what was my ground set going to be?
X belonging to all of the.
Good. Right. X is the whole space. Okay. Important thing to know. Okay? All right? So That's good now. So now we get the tricky part. So I'm not going to call on Andrew because he's the TA. So Dan, you're up. Okay? So Dan, what is L star of U?
Oh, it's going to be minimizing L of x u with respect to x for the u.
Right. So right. So x has to be just in Rn, and this is going to be B transpose U plus C minus A transpose U x. Okay. And what's that going to evaluate to? Okay. And now this is ROGs, right? Yeah. All right. So now ROGs. Let me ask you this: if A transpose U equals C, what does this evaluate to? Right. So that it's just going to be B transpose U if A transpose U equals C. Okay. And now, Jan, what if A transpose U is not equal to C? And now pay attention. What if A transpose U is not equal to C? What's it going to evaluate to? You're not sure. And you are Dan? No, Steve. Hybo. Sorry. Hope you'll rewind the tape. Hybo.
I think you can just set the derivative to the 0 and solve that.
Yeah. Okay. Take a look at that, though. Let me just ask you a question, Hybo. Suppose I have the following problem. Minimize 7x, subject to x is in R. What does this evaluate to?
Minus infinity.
Minus infinity. Now let me ask you this. What does this evaluate to when A transpose U is not equal to C?
Okay, yeah,
Yeah.
that's right.
It's minus infinity.
Yeah.
Right. In fact, that's what we did. We set the derivative equal to 0 here, but we couldn't set the derivative to 0. The derivative, the gradient, is C minus A transpose U. Okay. So that this is going to be minus infinity if A transpose U is not equal to C. Okay? All right, so that's L star of U. L star of U is B transpose U in this case, and it's minus infinity in this case. Okay, and now I've completely blown all my, Chihuahua. Okay, so Chihuahua, now what's the dual problem going to be? What's the dual? Now, I've done step 2, which is I got L star of U. Now I need to formulate the dual. Not sure where to go. Claire.
Just maximize the
Right, I want to maximize this expression, but of course, since I'm maximizing, A transpose U not equal to C evaluates to minus infinity. I might as well call that a constraint, right? From the discussion we had earlier. Okay, so I might as well sort of say, well, in fact, A transpose U had better equal to C down here. And what's the objective function? B transpose U. And what's the other constraint? Take a look over there. U greater than or equal to 0. Right? And now notice, fortunately, that's identical to this, just with a change of name. Okay? All right, good. All right, so I just want you to see, in fact, now, I think one of your homework exercises is to do something like the following. So, like, this looks like a lot of homework, right? But it's not, because I never give you a lot of homework, right? Well, I don't know about that. But, oh, I think there's a mistake here. This should be a 3. Sorry. Sorry about that. My pen got a little faster. Let me just make sure of that. Hold on. Yep. Okay. Now it looks like a lot of homework. All right. But most of these are just constructing duals. Okay, just to give you some calisthenic exercise. Okay. Of course, ladies and gentlemen, if my LP looked like this, then I could do a bunch of things, right? I could sort of call this the constraints and this the ground set. I could call both of these the constraints and keep Rn as the ground set. Okay, I could even call these the constraints and this the ground set, although that's not going to get you very far. Okay, so how do I know? How do I know that? Because I've been taking duals for 20 years. That's how I know it. Okay, and actually I should point out this duality theory I learned my second year at MIT. Okay, so the duality theory I learned as a doctoral student was something called Fenchel duality. How many of you have ever heard of that? Claire has heard of it. Okay, so Fenchel duality is a very, very abstract framework. Anyway, I learned of this after I came here. So the point is, though, for the LP case, if you do it right, okay, all your duals look the same by the time you're done. Okay, and that's just the LP case. And you're asked, I think in one of the homework exercises, to take the dual of this a couple of different ways and to see what happens. Oops. Hello? All right, let's do another one, since we're having such a good time. Okay. Let's look at the following problem. And I'm going to abstract a little from problem 5.3. I'm going to look at minimize Cx subject to Ax equal b, x positive, minus the sum of the log of the x's. Okay? So that's going to be my problem. Okay? Now, typically, ladies and gentlemen, when we try and formulate dual problems, we're looking for constraints that get in the way of conveniently solving things. Okay? What constraints get in the way of conveniently solving this problem? Actually, you know what? Even before we do this, I'm going to do something on the side here. I think I'm going to call on Hybo to do this. Hybo, since you're our man in... Didn't this happen once before? When I was having a very bad day. Yeah. I got one eraser left. Okay. So, Hypo, suppose my problem was this. Minimize 7x minus log of x. Okay? How do I solve that problem? This is not tricky at all. Okay? X is in R.
Then we can just set the derivative to 0.
Good. And so I get, if I set the derivative equal to 0, what's the x going to be?
7 equals to 1 over x, x equals to 1 over 7.
X equals 1 over 7th will be the solution. And notice, then when I plug that back in here, x equals 1 over 7th, so that the minimum of this is going to be 1 minus the log of 1 over 7th, which is the same as 1 plus log of 7. Everybody see that? I did that a little fast, but it's only one-dimensional arithmetic here. Okay? All right, so let's just keep that mental arithmetic in mind. Okay? So, of course, I could apply the same thing here, because if I didn't have these constraints, I could just sort of say, well, if I set the derivatives of each component equal to 0, I'd get Cj minus 1 over xj is 0. Xj is then 1 over Cj, etc., etc. Everybody with me? Okay. So often when we try and formulate duals, and this is the creative part, okay, and this is the part where, in a sense, I can't so much teach you as show you by example. Okay? So we look for constraints that if I were to get them out of the constraints might simplify my problem. Okay? So let's do that here. So what constraints, I will get rid of these constraints. And now, of course, oh, that's right. This is ax equal b. So what do I do with ax equal b? Well, I could write it as ax less than or equal to b and minus ax less than or equal to minus b. But between you and I, let's just, instead of having the u's non-negative by the time we're done, let's just have u's be unrestricted in sign. Okay, is that fair enough? All right, we'll soon see that. So then, if that's the case, and who am I up to? I got to get my Gordons and my Peters straightened out. You are Gordon. It's one of those days. Somebody better hold this eraser so it... Jason, that's right. Ah, brother. All right. So Jason, what does my Lagrangian looks like then for this problem? Mm-hmm. All right. It didn't really matter which order we did them, right? Since they're unrestricted, but I'm going to put the b with the plus sign. Why? Because I want to do it that way. And for no other reason. Okay, because it could go either way. Okay? And then I can rearrange this to be B transpose U plus C minus A transpose U Tx minus the sum of the log of the xj's. Okay? And now, your name begins with a T.
Alp.
Alp. You're from Turkey, right?
Yeah,
Begins with a T. Okay. What?
That's correct.
Yes. All right. All right, Alp. How do I solve this? So sorry. So L star of U, that's right, is going to be the minimum of this. X positive. So you think of X positive as my ground set. But actually, before you even do that, I'm going to go back to Hybo for a minute. So Hybo, you did a great job here on this minimize 7x. I got it right? Yeah, okay. Minimize 7x minus the log of x. Okay. Now Hybo, what if this 7 was instead minus 4? What does this evaluate to then?
Well, it's just this negative, minus infinity.
Minus infinity, right? Notice, if I have a negative number here, just by making x bigger and bigger and bigger, I drive this more negative, and I drive this more negative. Okay. In fact, if I have a 0 here, this also evaluates to minus infinity. Okay? Everybody see that? Okay. Alp, you're on. So now what do I do down here?
Gradient equal to 0.
Set the gradient equal to 0, but I need to maintain, so let's just almost do it component-wise. Okay? So because you can think about this is separable in each component of x, right? Because this is just sum of the components of this times their each individual xj's minus the sum of the log of the x's. Okay? And what do I need for this to not evaluate to minus infinity?
X greater than 0.
No, not x greater than 0. Karine has it. That's right. So that if C minus A transpose U, okay, is not bigger than 0, this is going to evaluate to minus infinity. Okay? One of the components here is going to be 0 or negative, and by Hybo's argument over here, I can just drive that down to minus infinity by kicking that component of x as high as I want. Everybody following me? Okay. Again, ladies and gentlemen, right, this is some of the art. Right? I'm not doing anything involving any depth here. I'm just doing things, though, that I know how to think, and now I want to show you how to think in creating duals. All right? So when C minus A transpose U is positive, then I'm going to be able to go to work on this problem. Okay? And now, Teresa, help me get to work here. Let's do it component-wise. Actually, let's do it component-wise. Let's do it, since this separates out, So what's the derivative going to be for the jth component? C minus 8tu sub j, yeah, equals 0. So then what's xj going to equal to?
1 over C minus 18.
Right. Okay. And now, so notice I'm doing this offline. I literally have to go get out another pad of paper, do some scratch work, see what happens, and then I'm going to plug in the answer over here of what the answer is going to be. Okay. That's how I'm going to do this. Okay. So Teresa, you're doing such a good job. I want you to continue. So if I plug this in for each component over here, so let's try and think. Well, first of all, let me just, right, so we're going to get the BTU. That was the easy part. Okay. And this was ATU, no, C minus ATU positive. Okay. And when I plug in 1 over, xj is 1 over this, into this term, what am I going to get?
You're going to get the C minus ATU I plus the J XJ.
Okay. Peter, can you help Teresa? I don't think you've said anything wrong, but we can, go ahead. N. That's right, I'm going to get N. Right, because each of these components is going to have C minus A transpose U in the numerator, and sub j, and then C minus A transpose U sub j in the denominator for each component. Everybody with me? Okay. I'll have N of those, so that's this part. And then what's this going to be?
You guys with me?
Yeah.
Oh. Minus the sum of
Don't write this down, even though you're correct. Don't worry. Go ahead.
the log, plus the sum
Good.
of C minus
ATU sub j. Right. Isn't that nice? So that is, right, because this was in the denominator, and by the rules of logarithms, then the minus cancels with that and everything, and so we wind up with this. Okay. And so, Elisa, let's write down the dual in all its beauty. It's going to be
So you want to maximize
uh-huh.
ETU
Right.
plus N,
Good.
and then the sum of log, or the log of that.
Okay. Good. The sum of the logs of the C minus A transpose U sub j. Okay.
And then C minus ATU.
Good. Okay. That's the dual of that problem. Okay. Peter.
That's right. When we were writing down L star U,
Yeah.
we had the constraint that x had to be greater than 0. So how do we know that? Oh, never mind.
Because we did it right here,
Yeah.
right?
Yeah.
And everything. No, it's the right question to ask. Good question to ask, and it all works out. Okay. Okay. So now, in the homeworks, and we'll see some other stuff, you'll be asked to do, you're asked to compute some duals or to formulate some duals, okay, for a bunch of different problems. All right?
I'm still confused with that. If you have a complicated set,
Yeah.
x, how does it get transformed?
Well, then you're going to have some trouble. In other words, that's what I'm saying. This theory only remains theory unless this thing lends itself to some constructive evaluation. If I can't constructively evaluate this, then I'm left just with theory. Okay? But there's sort of there's a halfway house too, which is, suppose for example, L star of U, while it doesn't have a closed form solution, it's like the solution to a network flow problem. Well, that's such an easy problem. I might just sort of say, that's what it is, and I'll design algorithms based on it. Okay. That's what I'm saying. You can always write down a dual, but is it really, can you really see what it is? And not always. All right. Very good. So then on page 10, I just have this quick note. right? That if I have problems with different formats, everything works out in the usual way from linear programming. So for example, if the problem looked like this, I have minimize a of x. I got a bunch of gi of x is less than or equal to 0 for I in some index set L, where L is less than or equal to. Gi of x, say, is equal to 0 for I in E. And gi of x is bigger than or equal to 0 for I in capital G. I formulate the Lagrangian for this problem as just what you would think would be f of x plus some I in L ui gi of x plus some I in E ui gi of x plus some I in G ui gi of x. Okay. I solve for my dual function, but my dual problem then is maximize L star of u, where u now is the ui's are non-negative for I in L. They're less than or equal to 0 for I in G. And I write it this way. This is just sort of a reminder. They're unrestricted in sign. So they're bigger than or less than 0. Okay?
Non-zero.
Huh?
They are non-zero.
Oh, they could be
They
0.
could be 0.
They're just completely unrestricted. Okay? Yeah. All right. All right. So now, let's look at the geometry of the dual. Okay? Now, the geometry of the dual, we're going to work in a space. This is, oddly enough, this is the... We're going to work in a space called the column geometry of optimization. It's a space most people don't view things in anymore. Okay? But let me ask those of you, now, all of you but a couple of you, who here has not taken a course in linear programming? Too many of you. Wow. Okay, so, all right. So, all right, well, let me ask you this then. So wait, raise your hands again. All right. So Rachel, why do I change the sign here? You don't know, right? You just believed it because it was in print. Okay.
We've seen it work through.
That's right, right. You could sort of think,
It's always worked out.
yeah, so that, right, if gi of x is less than or equal to 0, I could take this constraint, I could convert it to less than or equal to by multiplying through by minus 1, right? And then I would have my multiplier would be non-negative, but it would be, if I wanted to think of it, but then in here, I'd have the way it all works out, it just works out that way. And then if equality constraints, I can always write down as gi of x is less than or equal to 0 and minus gi of x is less than or equal to 0. And so by the time you're done doing that, you wind up with a dual variable that is the difference of two non-negative numbers, which is whatever it could, whatever. Okay, so that's how it all works out. Okay, now those of you who've had linear programming, you've heard of the simplex method, right? How many of you know why the simplex method is called the simplex method? What are they teaching you young whippersnappers these days? Okay, none of you know this? Okay, Dan knows it, and Tim knows it, and Pravitha knows it. Okay, so Tim, why is it called the simplex method? Do you remember?
Because the object that you're really considering is a simplex, and you're moving through this simplex when you go from feasible solution to feasible solution.
Okay, that's actually not quite true. But it was a nice try. Okay, so as originally conceived, it was a simplex, but it was for a special format of linear programming. It was for ax equals 0, some of the x's equal 1. Okay, and then it was a simplex. Oh, I guess you could... Oh, take it back. If you look at it right, it's still a simplex. Anyway, this is all in the column geometry. So let's look at the column geometry of the dual. Okay? So the column geometry of the dual is going to look like this. Okay? I'm going to associate, think of a vector SZ, where S is S1 through SM, and then I have a Z down here. And you can think of this as being G1 of X through GM of X and F of X. Okay. I'm going to look in the space of what's called resource cost space. If I think of this problem as minimize cost, and I think of my constraints, I have, say, a constraint for each of my resources. Labor, steel, wood, whatever. Okay. I have a constraint for each of those. I'm going to look in resource cost space. All right? And I will define the following set. I'll let I be the set of all SZs such that there exists an X in X with G of X less than or equal to S and F of X less than or equal to Z. Okay, what's this going to look like? Well, it turns out I'm going to draw this in 2 dimensions. And you're going to think 2 dimensions isn't going to tell me anything. But it turns out all the intuition you need, pretty much, is in 2 dimensions. And that's actually fairly convenient. Okay? So the picture is going to look like this. You can think I have cost up here, and I have my resources here. Think of this as S and Z. Okay? So take a point in the ground set, okay? Compute its resource utilization, compute its cost, plot that point, say that's here. Okay? Notice it's not feasible for this problem because its resource utilization is positive. Okay, but I don't care about that right now. I'm looking at that set I. And then all resource utilization bigger than that and all costs bigger than that are where in this picture? Pravita. Above the point and to the right. Okay. Okay. So that's for that X. Okay. And in general, if I plotted it for all X's, I might have something looking like this in here. But whatever this set I looks like, okay, for every point in it, everything up and to the right also has to be in it. Okay? That's what it's going to look like. Okay? Now, did you have a homework exercise that asked you to show that when X was convex, the G's are convex and F is convex, that this is a convex set? I forget if I assigned that to you. You did? We did? Okay, good. All right. So that in fact, when my constraints are convex and my objective function is convex, this set I is going to be a convex set. Okay? I mean, if you don't remember proving it in your homework, it's like a 2-liner. There's nothing there. Okay? So, but this is generally what it's going to look like. Okay? So in fact, in the convex case, let's just draw it in the convex case. It's going to look something like this. Oh, let's have it go down all the way here. It's going to look something like this. That's going to be my set I. So it's going to be everything over here. Okay? And now, here's what I'm going to propose. Here's a game I'm going to propose we play. Okay? Let's try and think of all hyperplanes that lie below this set. Okay? So for example, here's a hyperplane that lies below the set. And let's try and think of the following problem. Of all hyperplanes that lie below the set, let's try and find that hyperplane that lies below the set whose intersection with this line is as high as possible. Okay? Just a game. Okay? Everybody see the solution? The solution is going to be like right, well, I kind of drew it funny. But you get the picture, right? That's it. Okay? All right. Guess what? Guess what? Craig. You don't know. Len.
Is there something important about the slope?
Yes, that's going to be the solution to the dual. And the game that I just described to you is the dual. Okay, so it turns out the dual is completely equivalent to what I just described to you. It's saying find the hyperplane below this set I whose intersection with this line is as high as possible. And let's do the derivation of that.
Is that line defined by 0 resources? Or how is that line?
That line is defined by 0 resources. That line is, and in fact, Peter, okay, that line is defined by this right-hand side. It's this 0, okay? So that's so it's not the 0 resources, it's the 0 right-hand side, okay? Actually, great question. All right, so let's prove that. So let's get some definitions going here. Yes?
Also, objective function, like the primal is to minimize the cost.
Right.
Here, why are you looking for a hyperplane that sort of maximizes the cost?
I'm maximizing the intersection with the line. I'm not that I haven't. The units associated with this is dollars, and say the units associated with this say is labor hours, or whatever. Okay, but that hey, I just got a dual here. I'm not. In specific instances, I can tell different stories, but the generic story is this geometric story. Okay, that's all. Dan.
So if we replace the surface that defines I with the hyperplane, will we get the same optimal solution for the primal?
No. I don't. Restate your question.
So it seems like the hyperplane is supporting I in such a way that we can get rid of I and just stick with the hyperplane. Okay, half space.
Hold on a second. I believe. Hold on. Wait, I just got to meditate on this for a second. The answer to your question is, if we replaced that with the hyperplane, all optimal solutions to their original problem would be optimal for this problem. Okay? But not the other way around. Okay? I think. Give me some time to think about that. Okay? All right. Okay. For the remainder of the course, please refrain from asking creative questions. Okay? All right. So, let's define a hyperplane with, you could think of it sort of with slope u, as this is going to be the set of all SZs in my resource cost space with UTS plus Z equals alpha. So alpha is the right-hand side. Now why did I say sort of slope u? What are the coefficients, all right? In this space, this is m plus 1 dimensional space, okay? My coefficients on S are the u's, and my coefficients on Z is 1. So if you just, sort of the vector u1 is really my slope, in a sense. All right, that's all. I just wanted you to just see that. So define that to be my hyperplane, okay? That to be a generic hyperplane. And I will want... And I'll have the following line. I'll have the following line in this space, the set of SZ, such that S equals 0. Okay? And Peter, that's this line right here. Okay? All right? And I will be looking for my set to sit on a particular side of this. So I could say HU alpha plus will be, did I get that right? Wait a minute. Yeah. HU alpha. I defined it differently here. Yeah, but that's fine. Whatever, doesn't matter. Okay. I will say that That's the half space I'm going to be interested in. So that I'll have my plane here, and I will want my set I to be on that half space. All right? So let's write that down. When I write that down, that's going to be, I need more blackboard here. I need a plan here. Hold on. All right, let's do it right here. Okay. So suppose I write down the following problem. I want to maximize alpha. So alpha is the intersection of this L with my original H, which had the equal here. Okay, but let's just leave it this way here. Maximize alpha such that H U alpha plus, okay, contains I. All right, that's really my problem. I want to maximize the intersection with that line alpha subject to my I is in this subspace, right? I mean, is in this half space. All right, let's write that down a little more formally. And then I'm on page 14, and you can see by the time we get down to the bottom of the page, I'm going to have the dual problem. So don't look there, just look at me. Okay? So this is really the first line on page 14. This means HU alpha is a lower support of I. But that's really the same as maximize alpha subject to, well, U transpose S plus Z is bigger than or equal to alpha for any SZ in I, by definition. I have done nothing deep from getting from this step to this step. I've just written down what this is, and this just means every SZ in I has to satisfy this inequality. Okay? But now notice, what does the sign of U have to be here? What is the vector U? What are the sign of each of its components must be, have to be? And I'm up to Gordon.
So, greater than or equal to 0?
Why?
Because we're forming the dual problem.
No, we haven't formulated anything.
I'm sorry.
Okay. We're not even doing the dual. So that is, by definition of I, if I have any S in I, okay, I can keep making S bigger and bigger and bigger and stay in I, can't I? So if I have some S that's in, if I have some SZ, that means there's some X, which S is bigger than or equal to G of X. I could keep cranking S up as high as I want. Remember, the way I drew S is regardless of what it looks like, I can always make, this was S and Z, I can always make S bigger and stay in there. And given that I can always make S bigger and stay in there, I can't have any U's with negative components. Because if any of these U's had a negative component, if I cranked up that S big enough, it would violate this. Okay? So in fact, I can also, I really should write U non-negative up here. Okay? And that being the case, all I need to consider are my UT G of X's plus F of X's bigger than or equal to alpha for any X in X. Right? Because if any of my S is bigger than my G's, if I set S equal to G of X and Z equal to F of X, okay, that's going to be in the set I. And once that's in there, then any S bigger than G and any Z bigger than F is also going to be in there. Okay? So I can write this way. All right? Well, now let me write this down here. But what is U transpose G of X, F of X? What do we know that as? And I'm up to Jeff.
That's the Lagrangian.
Good. So that this actually is maximize alpha over U non-negative L of XU bigger than or equal to alpha for any x in x. Okay? But what does this mean? Alan?
Minimizing a cost function?
Yeah, that is
Minimizing
the only way this is true is if this is really L star of u is bigger than or equal to alpha. Right? Because this has to be true for all x. That means it has to be true for the minimum over all x of Lx in u. Okay, and that's just L star of u. Okay? But now this, of course, this is just maximize L star of u, u non-negative. And that's the dual. Okay. I want you to know I've been talking to you now about duality for over an hour. I've introduced a lot of new ways to think and do constructions, but haven't done anything deep here. Right? In fact, the most deep thing we did was when Heibo took that derivative of the log and got 1 over x. That's the only powerful mathematics we've actually looked at here. Okay. In fact, I have made no assumptions about any of these objects up here. Now, in order to draw the nice, pretty convex picture, I had to assume things are convex, but that was just for the sake of drawing pretty pictures. So in fact, with that interpretation of the dual, if my set I looks like this, for this problem, is there a duality gap? Hamid? Yes. Right? Because if I try and get a line that's going to be the best support here, is going to have a little gap here. Okay? And so in fact, when my set I is not convex, I'm never going to be able to prove that there's no duality gap. And even when the set I is convex, bizarre things can happen. Now in the LP case, bizarre things cannot happen. But even in other cases, I can create for you very simple problems that by the time you get it in this form, well, actually, so let me first draw this is the well-behaved case. Okay? My set I is convex. My hyperplane comes through, touches here. Optimal solution to the primal, optimal solution to the dual. We all walk home. We all walk home very happy. No duality gap. Okay. So I will show you in a couple of weeks when we get into semi-definite programming a very simple problem for which by the time I draw this picture, it actually looks like this. Okay. So the value of the primal is here. But for this set, so this set, my I set is everything here, but it's closed here, but it's open here. What's the value of the dual here? Nicholas, you have no idea.
I guess you have still the duality gap.
Yeah, that is, all my planes are going to, the best I can do is right here. So there's going to be a duality gap. And notice, this set is a convex set. It is not a well-behaved convex set. Okay, but it's a convex set. So there's going to be some of that coming up. All right.
We can replace I with the hyperplane only if we have strong duality.
No, it's not even that. Don't.
Okay, sorry.
That's okay. No. These are good questions. These are good questions. Okay. So anyway, I say at the top of page 15, it says, right in italics, the dual problem corresponds to finding a hyperplane that is a lower support of I and whose intersection with L is the highest. The highest value is exactly the value of the dual problem, namely V star. Okay? All right, let's do a couple more things. The primal problem could be a mess. But according to page 15, the dual problem is a concave maximization problem. That's nice. Okay? So in fact, let me see. Let me do that over here. Okay? Oh, actually, before I leave that picture, for those few of you in the class who were good students and took linear programming before this class, okay, the dual variables in a linear program have what interpretation? Do you remember? They're shadow prices on what? On the constraints. On which aspect of the constraints?
The right-hand side.
The right-hand side. That's right. Now let's look at this canonical picture here. Okay? I cut through here. Okay. Now let me ask you this. If I change this right-hand side a little bit from 0, right, the value of my... Oh, by the way, I never got to the value of the primal. Sorry. So the value of the dual was this maximum height. Why is the value of the primal... That's right, you guys were confused on it. So suppose my problem looks like this. What's the value of the primal problem? Here. I never did this, I'm sorry. Anybody see the value of the primal problem in here?
Just the intersection.
It's actually, you can think of it as it is the lowest point. It is the lowest point on this set. Okay, why is that? So this is a funny thing because we're not in primal space. We're in resource cost space. So you're thinking, okay, if I want to look at the primal problem, I plot my feasible region and I see what's happening. We're not doing that here. I'm saying each point here, each point in my set I corresponds to a resource and cost utilization that's at least as large as that for some x. Right? I should kind of rewrite my I set here. Some x in my ground set with f of x less than or equal to z, g of x less than or equal to s. And you can think of it as take all my x's, plot them, and then build that envelope up and to the right for each of those. Okay? So in particular, this point here is a resource cost utilization for some x in the ground set. Everybody with me? Okay? And hence, and so is this one. But the resource cost utilization for the x that gives me this is not feasible for the original problem because its resource utilization is positive as opposed to less than or equal to 0. Okay? So it's the ones over here that correspond to being feasible. And among those that are over here, everything here has resource utilization that's less than or equal to 0. And the one that has the resource utilization less than or equal to 0 with the lowest cost is right here. Okay, Claire?
I'm just not used to that terminology. Like, I know the costs are the multipliers themselves.
Yeah.
The resources.
No, don't think of them that way. Think of them as, when costs, I literally mean my objective function. So if my objective function was, minimize the dollars that I'm spending, then it's cost. If my objective function was minimize the energy in my truss, then it's whatever units of energy are. Dynes or ergs or furlongs, something like that. It's not a furlong. Huh?
Then what's the resource?
So the resource, you can think of, so
Is X?
no, that's my, like I said, if you want to think of the canonical story here, think of minimized cost subject to my net labor utilization has to be less than or equal to 0.
So the resources are the constraint.
Yes, resources are the constraints. Right. Okay. So that's the solution to the primal. And then for this one, of course, the dual solution is going to be, somewhere here. And there's a duality gap. It turns out duality gaps actually, you sort of think, oh, what a horrible theory, there's duality gaps. Well, it's not such a horrible theory because it turns out we build these duals when we solve hard combinatorial optimization problems. We get good dual solutions that tell us we're guaranteed within 2% of being optimum, and then we decide that's good enough for me, and we walk home. Okay? And that's one of the very powerful uses of duality theory, is constructing bounds for combinatorial problems. Okay? Very useful. I can't emphasize that enough. Okay? And you sort of think, well, then that's going to rely on us having to solve the dual. But it turns out that the dual, in a way, is better structured than the primal. Now, it can't be too better structured. That is, you're not going to have a primal problem that's nonlinear, and then its dual is going to be an LP. Okay? And actually, I'll tell you a story about that. You think, here's another one of Rob's stories. Okay? But this is a true story. So how many of you have heard of the mathematician David Gale? Not from the movie, The Life of David. So David Gale worked with Kuhn and Tucker. He's a member of the National Academy of Sciences. He did what's called Gale. Actually, he's more in a math department at Berkeley. So he did what's called Gale diagrams for polyhedra. So anyway, David Gale was messing around in the late 70s one afternoon on this very complicated geometric arrangement problem. He took the dual. The dual was a quadratic program, and he was very surprised to see that, in fact, you could actually solve this dual using ordinary convex quadratic programming methods. Okay, so I guess he had been out of optimization for a while, because if he had known, if the dual is a quadratic program, the primal is a quadratic program. And it turns out there was an elementary transformation that transformed his very complicated problem, the primal, into a convex quadratic program. He wrote a paper on this and was very excited about it and shared it with my advisor. My advisor showed it to me. I sort of said, no, look, this thing's got to be a QP. And I came up with the transformation, and my advisor said, you should call David Gale. He'll be very upset and very angry, but he will be grateful that you will have saved him a ton of embarrassment. So I did, and he got very ticked off. He asked who I was, what business I was doing. It was a horrible interchange. And then my advisor said, you really should write this up yourself as something. But then I found out over the next week. This is Andrew, you should. And those of you that have advisors, there's an important lesson in this. My advisor got very excited about this work I was doing on this, and but then I found out over the weekend that this all had been done 20 years earlier, and I was very disappointed, but I had my own little grin on my face, because when I went to see my advisor, I said, this was all done earlier in the chapter of a book that you edited. So anyway, I met David Gale a year later at a dinner party, and I was sitting with him and with my advisor. And he turned to my advisor. We were having some delightful conversation. And he turned to my advisor. He'd go, did you have some other student who was like really obnoxious? This is true. All right. So the dual problem, in a sense, can't be so fantastic, okay? But it will always be a concave optimization problem, okay? And that is great, because even if the original problem is like NP complete, the dual problem, in a sense, is structurally doable, because it's essentially a convex programming, because we're maximizing a concave function. So let's just see why L star of u must be concave. Okay? So, and that's theorem 7.1. So watch. Okay? So L star of u is concave, and here's the proof. Okay? So pick, say, u1 non-negative, u2 non-negative, and let u be some convex combination of u1 and u2. Okay? Then, continuing the proof on the next blackboard, works like this. L star of u, okay, is going to be, by definition, the minimum over all x in x, f of x plus, well, it's going to be lambda u1 plus 1 minus lambda u2 transpose g of x. Right? But now I can rewrite this as this is the minimum over all x in x of lambda f of x plus u1 transpose g of x plus 1 minus lambda times f of x plus u2 g of x. Right? Everybody see that? I've done nothing deep there. Except that I need to put something here and here. Okay? So now let me just rearrange this a little more. Actually, I'm just going to... We're all getting tired, so let me just do it this way. I'm going to pull this lambda out. No, I'm not going to do that. Yeah. So then this is... Now, I'm minimizing over all x in x, lambda times this expression plus 1 minus lambda times this expression. Okay? That is definitely going to be less than or equal to... Well, you didn't know what I was going to say. Okay. It's less than or equal to plus infinity. But bigger than or equal to... Okay. All right. If I did these separately, okay? So it's, and I'm just going to do it here. So plus the minimum over x in x. So now it's bigger than or equal to. Okay? And then I pull the lambdas and the 1 minus lambdas out. And so that's going to be lambda times the minimum of f of x plus u1 g of x plus 1 minus lambda minimum, you know, this is x in x, f of x plus u2 g of x. Okay? And that's just going to be, that's lambda L star of u1 plus 1 minus lambda L star of u2. Okay? And so that's the proof of concavity. Okay? And so in fact, even when the primal is a mess, okay, the dual will be a concave problem. Now, that raises a couple of issues computationally, which is, so if my primal problem is some horrible mixed integer program or whatever, okay, I can get good dual bounds if I can get good dual solutions. And so we will actually study, at least according to my syllabus, this is now new turf for me, so I hope we'll have the right amount of time for it, okay, 2 algorithms designed specifically for solving dual problems. Okay. And when are these algorithms used? These algorithms are used in discrete optimization to get good bounds. Okay. So anyway, that's where we're going. Let me just tell you what we're headed on Thursday. Okay. We're going to prove weak duality, which is a piece of cake. That's like a 2-liner. Okay. So there will always be, according to that picture, so the primal will always be at least as large as the dual. Okay. Then we're going to look at conditions under which strong duality hold. And we're going to pepper all of this with lots of examples. And you will see certain structured problems that naturally lend itself to tackling them via the dual. Anyway, that's that. I'll see you Thursday.